Hello everyone, this is Dr. Lennon, and we're going to go over some examples from homework number 5. So this goes back to implicit differentiation. Actually starts with chain rule problems and then goes on to implicit differentiation. So the first example that was requested, we just want to find the derivative. And again, this is a chain rule, so we want to have an inside function and an outside function. So again, the inside function is just what's in the exponent, because that's what we do first in an order of operations situation. So that's going to be 9 square root of x. And remember, when we differentiate, a lot of times it's helpful to rewrite the square root as an exponent. And then our outside function here is what we would get if we replace that 9 square root of x with another letter, let's say t. So it would be, it would be e to the t. So we would have e to the t power. And then the derivative of the inside here would be, again, we bring down the 1/2, we multiply that by the 9, and then we subtract 1 from the exponent. So this can be rewritten as, let's say, 4.5 divided by x to the 1/2 power. Or if you want to go back to the square root, you can write that as 4.5 divided by the square root of x, however you prefer. And then the derivative of the outside, the derivative of e to the t is just e to the t. So then how do we get our derivative? Well, we just multiply inside prime by outside prime. So I'm gonna multiply those two, and I need to change t back to what it represented initially, which is 9 times the square root of x. So I'm gonna get 4.5 divided by the square root of x times e raised to the 9 square root x. And that is my derivative for this problem. They may have left it as 9 over 2 instead of 4.5 square root of x. That would essentially be the same thing. So you may see them write it as 9 over 2 square root x times e to the 9 square root x. That's essentially the same thing. So if you want to do 9 over 2 as a decimal, or if you just want to leave it as a simplified fraction, it doesn't really matter. Either one of those is going to be fine. Okay, so let's go to the next example. The next example is actually very easy. Probably if you missed this one, you were just overthinking it. This is not even a chain rule problem per se, because we looked at the shortcut for an exponential derivative and standard form. So recall, if you're trying to take the derivative of some just base raised to a variable, b to the x, this would just be the natural log of b times b to the x. So if we're looking at this f of t, then f prime of t is just going to be so 5 is acting like our base for the first term. So it's going to be the natural log of 5 times 5 to the t power. And then the derivative of the 8, since it's not multiplied by a function of x, is just 0. So this is just a one-step problem if we remember the derivative formula for standard exponential functions. Okay, so the last two examples are just implicit differentiation examples. So we want to find y prime using implicit differentiation. So the derivative of the right-hand side here is easy. So 6x has an easy derivative, but for each of the first two terms, we need a product rule because we have a function of x multiplied by a function of y, and then for this one, we also need a product rule. So the first product rule, let's find its derivative. So remember, what we would call there u is x squared, and v we would call y. So u squared would be, or u prime would be the derivative of x squared, which is 2x, and the derivative of v, right, we're thinking of y as a function, so the derivative is not 1. We're going to think of it as just y prime, and then that's what we're going to try and solve for. So our first product rule is going to be x squared y prime plus 2xy. So that's our first product rule. And then our second product rule is going to have a similar setup, but remember this one we're multiplying now x times y squared. So u is equal to x for this one, v is equal to y squared. So u prime is 1. And when we take the derivative of y squared, we do it like normal, but then we just multiply by y prime using due to the chain rule, since we're thinking of it as a function of some implicit variable t. So we're going to write this as 2 times y, the normal derivative, but then again I multiply by a y prime. So my second product rule gives me, so u prime times v is just y squared, and then I add that to u times v prime, so that's x times 2y y prime, which I'm going to write, so x, I'll write it down like this, 2y y prime. But usually you kind of write things constants all the way in front, so I wrote an equals, I mean a plus there. So I'm going to write it instead as plus 2xy y prime. I just prefer to write it in that order. And then, so what we want to do is we want to plug both of those in. So that's kind of scratch work for figuring out the derivative on the left-hand side. The derivative of the left-hand side, we're just going to add those two things. So we're going to have x squared y prime plus 2xy plus y squared plus 2xy times y prime. And then the derivative of the right-hand 6x is just 6. So what we want to do is we want to move the terms that contain the that do not contain a y prime to the right-hand side of the equation. So those are the two middle terms here. They have no y prime, so I want to subtract them. So I'm subtracting 2xy and also subtracting y squared. So I do that on the other side. They're not like terms, so they're just going to end up being written behind the 6. So I have x squared y prime plus 2xy y prime, and that will equal 6 minus 2xy minus y squared. So then what I need to do is just factor out the y prime on the left. So if I factor out the y prime, I'm going to have two things inside the parentheses. So y prime, the first term, is just being multiplied by x squared, and then the second term, y prime, is being multiplied by 2xy. And then on the right-hand side, I just copy that down again. And now that I've got y prime being multiplied by x squared plus 2xy, I just divide by that parenthetical quantity. So I'm dividing by x squared plus 2xy. So I do that on both sides. And as mentioned, you know, these implicit differentiation formulas aren't necessarily going to be so clean. A lot of times they'll be messy, and they will typically involve both variables x and y, because we cannot solve for y explicitly. So that's the whole reason for this technique. So that is our answer for this third example. Okay, so the next example, let's look at that. So the very last one. We want to find the equation of a tangent line, and we're given a function that we can't solve for y, so we're going to have to use implicit differentiation. And as I noted before, anytime you're trying to find the equation of a tangent line, when you're using implicit differentiation, you can't be given typically just an x value, because if you're given just an x value, you might not be able to solve for a particular y value. So usually when you're asked to find the equation of a tangent line, and you have one of these curves that's not a function, you're going to have both coordinates of the ordered pair, both x and y. So let's go ahead and do the implicit differentiation. There's only one term that's multiplying x's and y's together, so this xy right here is going to require the product rule. So it's pretty similar to the last example, but even easier actually. So let's write down that product rule for the middle term. So how does that go? Well, we let u be x, we let v be y, u prime is 1, v prime is y prime, so our derivative here is y plus xy prime. So that's the product rule for the middle term. So That's just kind of scratch work off to the side. So let's go ahead and take the derivative. So the derivative, if you do 4x squared, that has derivative 4 times 2x, or 8x. The product rule that we found is y plus xy prime. And the derivative of 4y squared is going to be 8y times a y prime. And the derivative of 9, it being a constant, not being multiplied by a function of x or a function of y, it just goes to 0. Again, we want to move all the terms that don't contain a y prime to the other side of the equation. So we need to subtract both 8x and y. So we have xy prime plus 8y y prime equals minus 8x minus y. So we have to factor out our y prime. So we have x plus 8, and that will equal minus 8x minus y. And then we divide by the x plus 8 on both sides to solve for y prime. So divide by x plus 8. So our y prime is equal to minus 8x minus y divided by x plus 8. So why is that important? Well, if you have the derivative, that's a slope machine, essentially, right? If you can plug in an ordered pair, it tells you a slope. So if we plug 1, 1 into y prime, then we have the slope of the tangent line. So our slope, m, is equal to minus 8 times 1 minus 1 divided by 1 plus 8. So that comes out to negative 9 divided by 9, which is just negative 1. Okay, so to find the equation of our line, what we have to do is we have to, basically we know our line looks like y equals mx plus b, which is just negative 1 times x plus b, and then plug in 1, 1, use our point again to find b. So 1 equals minus 1 plus b, add 1 to both sides, so we get b equals 2. So that means the tangent line has equation y equals minus x plus 2. So this is our final answer there. And a lot of times when you have a function or a relation and a tangent line, I usually like to just check on some graphing utility that in fact it looks like it's tangent. So let's go ahead and do that. Let's go to Desmos, my favorite graphing utility, and try to plug those values in. So we have our first curve, 4x squared plus xy plus 4y squared, and that equals 9. So we've kind of got this weird kind of oval looking shape. It's probably an ellipse actually. And then we want to look at the equation of our tangent line, which is y equals minus x plus 2. And as we can see, that is perfectly tangent to our ellipse at the point 1, 1. So that worked out. So anyway, those are the 4 examples that students had questions about on the 5th homework. So if you have any others, please send them to me over the weekend, and I will be sure to answer them on Monday. Otherwise, this is Dr. Lennon signing off.